In the last video, we introduced the Maclaurin series. In that particular video, we worked through and found the general result for e to the x, so the Maclaurin expansion of e to the x. In this video, we're going to start looking at the natural log. So, if we start with the natural log and we take the f of x is equal to the natural log of x. If we take the derivative f dashed of x, we're going to get 1 over x, or x to the minus 1. The second derivative, f double dashed of x, will be equal to minus x to the minus 2. Let's just consider the Maclaurin expansion. It's given as the f of x is equal to the f of 0 plus f dashed of 0 multiplied by x plus f double dashed of 0 multiplied by x squared over 2 factorial. Then we go on, and then we'll have the rth derivative of 0 of x to the r over r factorial, and so on and so forth. If we now consider doing the f of 0 right here, this gives me now the f of 0 would be equal to the natural log of 0, which is undefined. So we cannot find a Maclaurin expansion for the natural log of x. What we do to get around this is take the function itself, and we say that the function is going to be the f of x will be equal to the natural log of 1 plus x. We need to ensure that we are restricting x for values between -1 and +1. It's inclusive, not of x, why do I want to put x? I want to put 1. It's inclusive of +1, but excludes -1. Whereas the video that we did previously, when we looked at e to the x is defined for all values. So now let's work with this one. What we're going to do is manually find the Maclaurin expansion of the natural log of 1 plus x. Then we'll get a general result and we'll look at it on a graph. So f of x is equal to the natural log of 1 plus x. The derivative f dashed of x will be now 1 over 1 plus x, which I'm going to write as 1 plus x to the minus 1. Second derivative, f double dashed of x, we're now going to get minus 1 plus x to the minus 2. All we're doing is applying the chain rule here, so we're just doing simple chain rule applications each time, and I'm assuming you're cool with that. So taking the fourth derivative, again using Roman numerals, we're going to have minus 6, 1 plus x to the minus 4. We know this is what we need for the Maclaurin expansion, so we need to evaluate the f of 0. The f of 0 is going to give us the natural log of 1 plus 0, or the natural log of 1. This corresponds to the term here. Natural log of 1 is 0. F dashed of 0 is going to give me now 1 plus 0 to the minus 1, which is 1 to the minus 1, which of course is 1. Second derivative, f double dashed of 0, is going to give me minus, and then we're going to have 1 to the minus 2, which gives me minus 1. The third derivative, f triple dashed of 0, is going to be 2 lots of 1 to the minus 3, which of course is going to give us 2. If we now go to the fourth derivative at 0, we're going to end up now with minus 6 lots of 1 to the minus 4, which gives us minus 6. We can now piece this together by using the Maclaurin expansion. The f of 0 plus f dash of 0 multiplied by x plus f double dash of 0 multiplied by x squared over 2 factorial, and so on and so forth. So if you want to scribble that down and have a go at this one, please do. So what we'll do, we'll build this up. So what we can say then is a natural log of 1 plus x, define the values of x between negative and positive 1, inclusive of positive 1. We can say this is going to be the f of 0, which is going to be 0. Then we're going to have f dash of 0 multiplied by x. That just gives me 1 times by x. So f dash 0 multiplied by x is going to give me plus 1x. Then we do f double dash of 0 multiplied by x squared over 2 factorial, which will give me now minus x squared over 2. Okay. If we now take the next one, f triple dash of 0 multiplied by x cubed over 3 factorial. So we end up with 2x cubed over 3 factorial. 3 factorial is 6. So we're going to wind up now with x cubed over 3. The next one, what we're going to have is f, the fourth derivative of f, so f to the fourth derivative. I don't think f to the fourth sounds too good. No, it's awful actually. The fourth derivative of 0 gives us now minus 6, so we're going to have minus 6x to the fourth over 4 factorial. 4 factorial now is 24. 6 over 24 will give us now 1 over 4. So this becomes x to the 4th over 4. And this goes right the way up. And it's unlikely you'd be asked to do this, but it'll go dot, 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 and then you'll have plus, and it'll be minus 1, and then we'll have, let's remember this, r to the minus 1, and then we'll have x to the r over r. It's unlikely you'll require that bit. Essentially, we just work with this part here. But the full expansion, well, it's not full expansion, it'll keep going. But in general, the full formulae from memory, please do check that, so I'm pretty sure that works. I'm used to just using the first few terms. So if we wanted to write this out, what we could say is the natural log of 1 plus x will be equal now to x minus x squared over 2 factorial plus x cubed over 3. And in this term, we put 2 factorial. Generally, it's just 2. And then on here, x cubed over 3 minus x to the 4th over 4. Okay, dot, 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 dot. So that would be the expansion right there. So we've got rid of the 0. And that's the general result. What we'll now do is look at this in terms of a graph and see what it does. And we'll see why it's valid between negative and positive 1. So again, this app, I'm going to put the link to it on the video here. It's not mine. Someone else has done it, so I'll link you off. So we can see now all this is a natural log graph shifted 1 to the right. And our first approximation is x. That's a straight line through the origin. So it's not a good approximation. So let's now look. That's now a quadratic, cubic. So you can see that in the area from, around the neighbourhood of 0, it's not a bad approximation. And these are the kind of things we'll be given in an exam. Next one, quartic, quintic. And then you can see the more that we do, the more accurate that it's going. And it's converging. But as soon as we go to the 1, it's going to end up diverging and not, you can see, after that point there, it's going to not provide. And we've done a load in, and that is a lot of terms in the series. And you can see that this is only going to be valid from negative 1 to positive 1. And if we want to be approximating terms, let's just roll it right the way back. You can see the level of accuracy. Let's just think about the first, let's think about the first 3 terms. You can see the level of accuracy getting close to 1. We're losing it. So if we want to be moving away from x equals 0 using Maclaurin, it works in the neighbourhood, but if we're moving too far away, you can see that the approximation is going to be somewhat questionable. So we'd need to take more and more terms the further away we got from 0. So let's look at that now in action. We're asked to express the natural log of 1 plus x as an infinite series in ascending powers of x. That's what we did. That was what we ended up with. And we saw that that was approximate. We could say first, and let's have a look at next, using only the first 3 terms. Okay, so what we can say then is the natural log ln of 1 plus x is approximately equal now to x minus x squared over 2 plus x cubed over 3. They're the first 3 terms, so that's what we're going to use. What we've been asked to do, this is the first part now, I've only expressed the first 3 terms. We need to find estimates for natural log of 1.05, 1.25 and 1.8. Let's just consider then on the first one, what we'll do is take x to be 0.05. The next one we'll take x to be 0.25. And then we'll take x to be 0.8. And we know the further that we're going to get away from 0, the less accurate this is going to be. So if we think about what we want then, we could now say that the natural log, so the natural log of 1.05 will be equal to 0.05. Then we're going to have minus 0.05 squared over 2, and then we're going to have plus 0.05 cubed over 3. And all we're doing is subbing this in. So in my calculator, what I'll do is just put in my first. So we take this and I'll put this in as my answer. So that's now stored in as the answer. So what we're going to do from here is just set this up. So what I'll have is my answer minus my answer squared. So answer squared over 2. And then what we'll have now is plus now my answer cubed. So answer cubed. Okay, answer cubed over 3. And we end up getting this right here. So what's that going to give me? 0, so 4879. So 4879. Then what was it? 1, I think 1, 6, 6, 6, 6, 7. Have I remembered all of that? I don't think I will have done. Yeah, that's pretty good. Okay, now let's actually find now the natural log of 1.05. So 1.05, and we can see now if we write this out, let's see what we get. So what are we good? We're good on that, as you can see, if we match these up to 5 decimal places. So you can see it's pretty accurate. Yet as soon as we try the natural log of 1.25, you'll see it's less accurate. Yet if we take more and more terms in our expansion, we're going to get more of an accurate figure. So hopefully that gives you some idea on how you can use it. In an exam, you might be asked to use the expansion to evaluate this. You might be asked to differentiate it. But in general, if you're not, you can use the general result of the expansion. So there we go. The natural log of 1 plus x, valid from x equals -1 to +1, inclusive of both. We've looked at the exponential function e to the x, which is valid for all x. And in the next video, we'll go on to some trig functions.